The last topic we're going to look at in section 6.1 is determining the minimal sample size needed to obtain a certain level of confidence. If we take our old school formula from just a while ago, the margin of error formula of E, you can take and rearrange that formula algebraically and solve it for the variable n. And what we would find is that n would be equal to the quantity z critical times sigma divided by E whole thing squared. So if you know the level of confidence that you're looking for, and you know what your margin of error you're working with is, you can actually compute the minimal sample size n needed to obtain that level of confidence in a confidence interval. Keep in mind that this is just the minimal sample size and would in practice be the sample size that researchers would use when they were gathering data, etc. Certainly if you have a larger sample size, you will still get at least that level of confidence, if not more. But if you're fixated and if you need to at least reach a certain level of precision, this would be the smallest sample size you could use to guarantee that level of confidence in your work. In this setup, just like it was with confidence intervals, almost all of the information will be given to us. They'll tell us the margin of error. The standard deviation will also have to be given. The only difference, the only similarity is that the majority of the work will be wrapped around solving for this z critical value. For instance, let's suppose we want to find the minimal sample size n corresponding to a confidence level of 0.98. Let's suppose we have a population standard deviation, we'll call it sigma of 10.1, corresponding to a margin of error of 2. What would be our minimal sample size? Well, again, anytime you hear that buzzword minimal sample size, automatically the first thing you should do is go ahead and write down that formula. N equals ZC times sigma divided by E, and it's that entire quantity squared. Okay. We know sigma, that's 10.1. We are told the margin of error is 2. The only thing we would need left to compute this calculation would again be the value for ZC. If we want to be 98% confident, or 0.98, that means that 0.98 would lie between our negative ZC and our positive ZC. We want to find, let's say, the left z-score. If 0.98 is between, then 1 minus 0.98, which would be 0.02, will lie in the two tails combined. Because of symmetry, we can take half of that divided by 2, and we would find that the left tail area would be 0.01. From there, you're now going to use your normal CDF calculation. Second distribution, inverse norm, cumulative area of 0.01, mean of 0, standard deviation of 1. Hit paste, hit enter, and to 3 decimal places we would get negative 2.326, which we can round up, not round up, but make sure you change it to be positive. It'll change to be positive 2.326 for the Z critical score. I would highly recommend, especially as you're working in my stat lab, it's good practice in this section to probably take that Z-score out a few more places if you're able to when you do your N calculation. And the reason why I say that is anytime we round this N value and we use it in a further calculation, that rounding error gets compounded, and in this section that could create a pretty big deal. And the reason why it's going to be a big deal is the fact of the matter is that we're actually squaring something, and when you square errors, the overall total error you get at the end could be significant enough to throw off your final answer, so that it might not necessarily round to how my stat lab is looking for it. So my advice, when you're doing N in this section, anytime you're computing minimal sample size, try to write out as many of the digits of N as you can, just so when it's all said and done, it'll round to the correct spot. So in the notes, I just go to 2.326 times 10.1 divided by 2, and it's that entire fraction that needs to be squared. When you punch this into your calculator, it's a good idea to put the whole fraction in parentheses, 2.326 times 10.1 divided by 2, and parentheses, and then square. If you don't put this expression in parentheses, then what would happen is the square would only go on the 2, and it would square the denominator of the fraction instead of the entire quantity. An alternative way to do this is you could do it in steps. You could multiply the numerator together, divide that answer by your margin of error, and then square it at the end, and then that would also work too. But what we would come up with here would be a 137.97, which is going to bump up to 138. So what this would tell us in this context is that we would need a minimal sample size of 138 data values in order to guarantee a 98% confidence interval. Another comment, and this is going to be very, very important as it pertains to n. When it comes to rounding for n, we round it much like what we did class with back at the beginning of class, in so much that n must always be rounded up. So here is pretty straightforward. We got 137.9, so obviously this would round to 138. However, if we had worked this out, and let's say we got like 137.1 or 137.2, it's not going to follow the standard rounding rules. You must always round n up to the next integer. Let's take a look at one more example. In example 4, we're going to do a 90% and then a 99% confidence interval for the, the mean age of students enrolled at the college. They say that the estimate must be within 1 year. So it has to be accurate within plus or minus 1 year. When they say within, that's kind of a buzzword to let you know that that's going to be your margin of error. So for this problem, we're going to be working with a margin of error of 1. They tell us that the standard deviation of this population is 1.2. And in part A, we want to do the 90% confidence interval. Okay. So we want to determine minimal sample size. Again, you pick up on the directions. They say determine minimal sample size. So immediately we want to write down a formula for n. N is equal to ZC times sigma divided by E whole quantity squared. We've seen this one pop up a bunch. This is the third time we've already seen this now, so I'm not going to go back and rework it. But we know that corresponding to the 90% level of confidence, that should be a Z critical value of 1.645. So n is going to be ZC 1.645, and again, ideally you should take that out a few more places, times sigma, that's 1.2, divided by the margin of error, 1, and then we're going to square that. 0.645 times 1.2 divided by 1. I'm going to do it differently this time. Let me work out that part first. And now that's what's on the inside. I need to square that. And we would get 3.89-ish. But that's going to round up to a minimal sample size of 4. So for the 90%, we need a minimal sample size of 4. Let's now take a look and do this for the 99% confidence interval. The only thing that's going to change is the Z critical value. We need the Z critical that corresponds to the 99% level of confidence. If it's 99% between, that means that it's 1% on the outside. Those outsides together make up the 1%. So the left tail would be half of 1%, which would be half of a percent. So we go to inverse norm, 0.5%, that's 0.005. Remember, you're always moving the decimal spot 2 places to the left to go from percent to decimal. It's a Z-score, so it's 0 and 1. Go ahead and hit enter, and we would get a critical Z-score taking the positive value, 2.57. I'll just be brief in the notes and say 6. Again, when you're doing it at home or if you're doing it in my stat lab, take that out a few more places just to be safe so you don't have round off error. We now have our Z critical value, and we can now go ahead and plug it into our formula. ZC times sigma divided by E whole fraction squared. In this case, we would get a value of 9.5, which would round up to 10. So to obtain a 99% confidence interval, our minimal sample size would need to be at least 10. The last thing they're asking us for is to compare which confidence level requires the larger sample size. Well, the answer is the 99% confidence interval. At the end of the day, if you want to be more confident, the way you can be more confident is by having more information. Right? So to go from 90% confident to 99% confident, we needed to have a larger sample. And so the takeaway here is that a higher level of confidence will always require a larger sample size.